Okay, so good afternoon, and welcome to my talk. So I'm going to change a little bit the topic from, can you hear me? Okay. Is it good now? Okay, thank you. Okay, so I was saying we are going to change a little bit the topic from query processing and optimization benchmarking to handling schemas in graph databases. Okay, so first of all, there is a group actually led by LDBC, the Property Graph Schema Working Group. And we are currently carrying out a discussion about proposing a schema language for property graph. Well, a few years ago, with the people from Lyon, among which Alistair, who is there, we worked on a concise data definition language for Cypher, at the time on Neo4j 3.5. And we discussed what are the mechanisms for schema validation and evolution. At the same time, with my group and some master students, we started another thread, how to extract schemas from property graph instances. So assuming that we have schema-less instances, as it is the case right now, how we can infer the schemas for those instances. And this will be the focus of my talk. So, so what do we need? Do we need schema discovery, and why this is important for property graphs? Well, we know that where linked data is ubiquitous. We had many presentations today that were from industry that were discussing possible use cases for property graphs. This data is heterogeneous. It might come from different data sources and then needs to be integrated, and then is semi-structured. So, and graph databases are stores, NoSQL stores in which we can store and process graph data. Right now, there aren't a priori schema constraints, and this is a problem because each operation, such as, for instance, query optimization, data integration, data exploration, would need some constraints of this kind. And on the other hand, the property graph the property graph model lends itself very well to schema in a sense, and then it's amenable to schema discovery because it's a labeled multi-graph with key value properties attached to nodes and edges. So the first step for us was to extend a schema inference, which was initially done for JSON data model, to property graph. So in this work, we used a schema inference mechanism which doesn't consider hierarchies and is not able to infer complex types. It's based on the MapReduce paradigm, and so we can only cope with a label-oriented schema inference or a property-oriented schema inference. So either we extract the labels or we extract the properties. So it's a trade-off, and then this leads to situations in which if you look only at the properties, you will have some nodes that are unlabeled, so it gets you a lot of spurious nodes. And on the other hand, if you ignore the properties, then of course you will lose some information, so you will have a lot of information loss. So we asked ourselves how we can improve this. Well, we worked on an approach which is based on a statistical more statistical, which is based on a clustering algorithm, the hierarchical clustering algorithm. And we used the Gaussian mixture model, the GMM, to do the schema inference and to be able to combine a label and property information at the same time. And lately, we also extended this to the dynamic case. So in case we have insertions, for now, we only cover the case of insertions of nodes and edges in the graph instances, how to make the schema inference incremental without recomputing, if possible, without recomputing. In some cases, of course, recomputation is needed, but we want to recompute as less as possible the schema, and then we have also another version which is an optimization based on memoization and avoids redundant computation. So let me define briefly a property graph. Yeah, everyone in this room knows what it is, but just to recap. So we have a set of vertices and a set of edges, and these are disjoint. Then we have a function that associates each edge to a pair of nodes. We have a function lambda that associates vertices and edges with a set of labels. And then we have a function sigma that associates vertices and labels with the properties. So and of course, these key value pairs to edges and vertices. When we go to property graph schemas, so here in this work we consider so given a set of base types, we consider a schema a set of element types where we have L, which is a set of labels, K, which is a set of property names, O, which is the subset of optional property names, and EB, which is the set of element types that B extends. So if we consider the LDBC post-node instance, for instance, here, the base type is the post with the K, where K is the set of mandatory properties, and then the optional properties are language and content. And we don't have a subtype, so the set of subtypes is empty. So this is the LDBC property graph schema. Yeah, this is the ground truth that we can use to measure the quality of the schema inference algorithm. So how is our approach working? So given a property graph instance, we want to derive a property graph schema. So we have 3 steps. In the first step, we do pre-processing. So we compute the set of labels and their frequencies in the graph instance by using Cipher queries. Then, because clustering needs sampling, we do some sampling, and then we apply the hierarchical clustering algorithm, and we derive the schema. So this is a simplified pipeline. I will give more details in a minute. So we use GMM to discover hierarchical node types. So now before you are going to ask me, why do you use this instead, and then the hierarchical clustering algorithm instead of another clustering algorithm, I'm going to prevent the question by saying, we have baselines, okay? So we have compared with the HDB scan and which is the baseline. And the problem is that those other algorithms, yeah, HDB scan is probably the most popular in our community. Those algorithms, they are problematic because they obtain a lot of variance in the distribution of the labels. Then for each node label, we run this GMM algorithm to fit a mixture of normal distributions, and we use the resulting model for clustering. And then the process is iterative, so we are going to reiterate the procedure in each subcluster. Okay, so this is the base algorithm for the static case. So first of all, we are going to build a dictionary in which we collect node labels and their frequencies. Then for each label, we process the set of nodes with that label. And we build these reference-based types, or reference-based types are the most general types that contain, at each step, they are built from all of the node labels and account for the most frequent properties. So you have to imagine that you have like a parent type, and then you might have subtypes, and those subtypes, they contain less properties than the parent type. And starting from this, then we build the feature vector from similarity scores of all the nodes in C with respect to this reference-based type. And we use this feature vector to fit the GMM model. We tune the parameters for GMM using an expectation maximization algorithm. And then we run the hierarchical clustering, and we update this reference-based type with new types discovered, and then we record the obtained subclusters, and we iteratively recall the algorithm on the subclusters that have been obtained. So just as an example, for instance, on our post node that we were seeing before, if we run GMM, we will obtain two posts, post 1 and post 2, yeah? As shown in this example. So, and then we will use those two obtained posts to rerun the procedure as we said before. So the obtained schemas for LDBC, it looks like this, and as you can see now, we have inferred this post 1 and post 2 that of course differ because they have different properties, yeah? Okay, so we ran some experiment to measure the quality of the obtained schema, right? Because this is important, right? So we used the LDBC. We used also some real world data set. So the brain, neural network of a fly fruit, this neoprint data set, which is used in Neo4j, and then the COVID-19, the covidgraph.org, also powered by Neo4j. And these are real graphs, and then we use as benchmark LDBC. And as you can see, they have different characteristics. These graph instances, the biggest one is the COVID-19, and this was the snapshot from August 2021, because if you are looking at it now, the graph is bigger, of course. There have been other cases of COVID in the meanwhile. And then as you can see, these are the ground truths. Yeah, this is the ground truth, and there is no ground truth for COVID-19 because of that. Yeah, it's an evolving data set. So we compared also with the MapReduce approach. And with respect to MapReduce approach, we obtained 3 times more node types and up to 3 orders of magnitude more edge types and 7 orders of magnitude more subtype edges for one data set, MBCs, the neoprint data set, and up to double the hierarchy depth. In fact, in the MapReduce case, many nodes are spurious, as I was saying before. And the obtained schema is a high accuracy. As you can see here, there are different metrics. Rand index, MI, they measure the quality of the clustering algorithm. And then the usual precision recall and F1 that measures the accuracy with respect to ground truth. Then we measured also the runtime to see how long is it to obtain these schemas, yeah. And here you can see the numbers. And for the baseline, which is the MapReduce case, as you can see, the runtime is quite big, and for the 3 data sets, and so on the left hand side, and for GMM is quite reasonable, and for COVID. We didn't have the baseline due to the fact that the data set is evolving. So the speed up in terms of schema discovery with respect to the baseline are respectively 8 times speed up for LDBC and FIB25 and 5 times for MBCs. So now briefly, I'm going to discuss the two variants of the schema inference algorithms for the dynamic case. So for the dynamic case, we consider as a set delta of graph updates, so a set of nodes inserted into G, so only insertions for now. And for each node in delta, we are going to compute the similarity score with respect to the reference-based time and assign it to the cluster that maximizes this similarity. And of course, the performance depends on the size of delta and on the size of the clusters. And but this remains still robust in practice. Then we have an optimization. Instead of repeating the computation due to the new insertions of on all the subclusters, we just repeat on the subclusters that have been affected by the changes. And this entail using memoization and avoiding recursive calls in these subclusters. So avoiding redundant steps. And this is a trade-off between performance and obtained quality. This is a system that runs. It's open source. It can be used by everyone, and we are happy to help you if you are interested to use the system. And it will be demonstrated at VLDB in about 2 months. And here you can see the modules as I have explained. So we have this data processing, and then the static version and the dynamic version with the two variants. And in the system, you can explore the schema. You can see what are the updates on the obtained schema, and you can play with different data sets. So conclusion, DiscoPG is the first schema discovery approach for property graphs that accounts at the same time for both node labels and properties, and addresses previous SOTA limitations such as spurious types or incomplete types, and also while keeping the performances and good and the runtimes very low, and also superior accuracy. And we found that there are many things to do in this area. First of all, the extensibility to future standard property graph schema languages on which the corresponding LDBC working group is working when this schema language will be available. And then the fact that statistical methods are promising for this problem. Another perspective is the using graph embeddings to represent structural information, extend this to streaming graphs. For now, we have the incremental case, but we don't cover the streaming case, as I was saying before, because it would have, all these issues that we just discussed with Peter about the Windows-based semantics and so on. So it would be interesting to do this. So schema discovery for streaming graphs, streaming property graphs. And then with the property graph schema working group, we have worked last year. We had a paper in SIGMOD on PG keys for property graphs. So it would be good also to do a property graph schema, a property graph key discovery. And with this, I would like to thank you. And so please do not hesitate if you have questions.
Thanks, Angela. A question from Alistair.
Thanks. That's very interesting. What do you mean by spurious in this context?
Yeah, spurious, we mean, when you, not in this, so in the previous paper, let me show you. Let me go back. I don't know if people online can still see my screen because I hope so, yeah. Yeah, here. Okay, so spurious means that you have, if you only focus on property-oriented approach, you would have nodes that are unlabeled. This is so spurious types. They don't have labels, but they have properties attached to them. Okay. If you don't
Why does that make them spurious? Why aren't they just characterized by the properties as their attribution? Why doesn't that define the type?
Well, a type is defined as a combination of labels and properties, right? But in this method, you cannot combine them. Either you go with the labels or you go with properties, because it's based on map reduce. So in the map reduce step, what happens is that you infer the types in the map step, and then in the reduce step, you try to merge the types, okay? Now, either you focus on label or you focus on properties. If you focus on properties, you will get these unlabeled nodes with a bunch of properties. Yeah, this is what we call spurious types.
And you're trying to remove those in your...
No, we don't remove, it's just like this. So your schema is like this, and you have to measure
in
precision
the
and
subsequent
recall.
work, you're talking about reducing the incidence of spurious types, and that, how does that, I don't understand how that occurs given your
You don't
definition
get
of
spurious type if you use a method that considers at the same time properties and labels.
But if an element has, you know, an empty set of labels and it has some properties, then according to what you've just said, I think that means it's spuriously typed. But I mean, that could actually occur. I mean, that if you look at both, you have to be able to cope with the situation where there's, you know, an empty set of either of them actually.
But in that case, you would, this might occur, and the method captures it. But in that case, you would get a wrong unlabeled type with a set of properties. It's a subtype, right?
Yeah.
And there is no label, because you didn't consider the label at all in your method. So you just focused on properties in this case, which is the baseline. But in the current method, you might get nodes that are unlabeled, but because these are in the ground truth, so they exist like this.
Yeah.
Okay.
Okay.
I don't know if there are questions.
If you scroll down a bit.
Oh.
Yeah. No, we don't have any more questions. So Peter has one.
Thank you. Yeah, Angela, interesting talk. I haven't read the paper, if there is a paper yet. So I'm going to ask a detailed question. So I did some work a long time ago on RDF, and also aimed at finding kind of structure and you could say a schema. Yeah, a schema out of RDF triples. And we found so with the goal of actually finding co-occurring attributes or properties or whatever you want to call them, and labels, which are names for these classes. We did find very many spurious types, in fact, but in a different way. So because what in real kind of data sets, not those generated such as LDBC by a data generator, so synthetic data sets, but in real data sets, there is a lot of chaos. Certainly in RDF data, there's lots of also errors, of course, mislabeled things, you know. So and we would find, and also there is this question of kind of modeling, like modeling class hierarchies. So you may see lots of persons, but you might also see students, and you may see professors, or you may see, you know, you may see these people with more or less attributes in that case that might stem from them being member of a superclass or class. And finding these classes is then also a challenge. And yeah, we would see thousands, hundreds of thousands of candidates of structural elements, you know, possible classes and their members and their attributes and all that. So yeah, when you said spurious types, I kind of related to that. And the task was for us to, in that work, to find a concise schema that on the one hand covers a lot of data, or most of the data, or well, a very high percentage of the data, but yet still is human interpretable, hopefully.
Yeah.
So small, because humans' brain overflows at some point. So yeah, a database schema with 20,000 tables is not so nice, and property graph schemas with 20,000 classes is also not so nice.
No, but
So yeah, so
I fully agree with you.
So it's all about spurious types, but were the data sets that you were analyzing, they are all synthetic, or
No.
The LWC was synthetic.
LWC is synthetic, and we have the ground truth, right? For those small instances of the neoprint database data set, we have the ground truth. For the COVID-19, we don't have the ground truth. And as you said, to build the ground truth, you need humans, right? So that's a problem. Yeah. So as you see, I don't have typically in that data systems paper, we have like 15.
No, we did not find. Sorry, we did not find the ground truth in that other work that I mentioned.
Yeah.
The criterion was to find something without ground truth, but try to make it as concise as possible. So there was some kind of optimization criterion that was a balance between coverage and conciseness. And then there is a best solution in a way. You know, there is a Pareto curve, if you will.
Yeah, absolutely. Yeah. Well, minimality is an issue, but then you still have to measure the quality of the schema, of the obtained schema, right? I mean, like it's sense? Minimal, yes, it's concise. But
the coverage is
like but the coverage you
quality.
need some reference, right? I mean, you need something. Either the human would tell you what are the expected types, or you need the ground truth, right, to measure the coverage.
No. Because there may not be a ground truth in the first place, I would say, but there is just a huge graph that initially does not have structure, and afterwards you have a structure, and you may be happy with that. Well,
okay.
Matteo, that's a DEP paper. It's my only DEP paper.
Okay, we can discuss. Yeah, I mean, like. There are several ways. I mean, I think also having input, in a sense, we have coverage here, because when I said we have these queries that do the pre-processing in which you are going to, compute all the labels and their frequencies, then you have coverage of the graph instance. So if that is what you mean by coverage, then we have coverage. But I'll take a look at your paper, and you take a look at our paper, and we can discuss. Okay.
Okay. Thanks very much, Angela, again.
Thank you.